Sorry for the delay. So today's speakers is Erika Coppola from ICTP. Erika graduated in physics from University of L'Aquila, then moved to University of Reading for her PhD in meteorology. And then she came back first L'Aquila and then here at ICTP, where she's a research scientist. And her science, she focused on modeling, regional modeling, climate regional modeling, and the use of machine learning as climate simulators. And she's going to tell us all about it today.
Okay, thanks, and thanks for coming. So today I will try to introduce you to a field that maybe you are not so much familiar, that is how we do global and regional climate modeling, what does it mean, and why we need a downscaling procedure, what means the downscaling procedures, and how machine learning can help us today that could not do something that they could not do in the past. So to start with, because otherwise it would be impossible for you to understand, I was thinking to give you a little bit of background about the climate modeling. So just a brief history. So the modern meteorology and the climatology even more is a very, very young science, because at the time in the early 1900s, there was Birkness that already said that to predict the status of the atmosphere in the future, it's needed the accurate knowledge of the present status and the accurate knowledge of the fluid dynamic equation, that are the equations that you all use. But in that period, the knowledge was not enough to be able to predict the future, neither the near future nor the far future. So then later on, there were some other students, Margulis and Exner, that they were actually students from Boltzmann, and they tried to solve a series of theoretical problems, and they understood that for them it was impossible. And so they say that the weather forecast was something immoral, harmful to the reputation of a meteorologist, simply because they didn't succeed. And then finally there was Lamarck that again tried this attempt to solve this dynamic equation. And then he said at the end that if in our climate the cause of the change in the atmosphere are all, without exception, irregular, without periodicity, and indeterminable, it is absolutely useless to make meteorological observation. So basically they said we cannot do it, so it's not possible to do it. But this is, of course, not true. And then later on, there was Richardson, that is considered to be the father of the modern metrology. And then he wrote down the actual equation that we use today. Some of them were already known. And then he was deriving the rest. So for the first time, he was the first one in the history to introduce a numerical procedure. So he tried to discretize the equation on a grid. You can see there the grid. And this was really a perfect approach for the computer. But the computer, unfortunately, were not there at that time. And he decided to start to do it manually. So he tried to do the first forecast by using the paper and the pen. And he was doing this while waiting during the First World War. He was driving an ambulance. So in the long time he was waiting, he was trying to solve this equation.
So which equations he was solving?
The fluid dynamic equation that he thought were the one that could give us the forecast at a time step t+1. I will show you later what they are. So it was, and then he tried to do it, and he was completely wrong. So he was forecasting the status of the atmosphere 6 hours in ahead, and so he was trying to forecast the value of the pressure field, and he was wrong of 150 hectopascal. That is a lot for all the pressure level that he tried. But he was convinced that he was right and that the method was correct, but the problem was the initial condition. And today we know that he was right. So if we have not a good idea of the initial condition, then we can be really, really wrong. This is why, because the climate system is a chaotic system, and so it's really strongly dependent from the initial condition. So if we start our integration from some point that are, you say there is a pointer, maybe. Okay, so if we start our integration from a point very, very close in the space of the initial condition, and we integrate for our equation for a number of time steps, we can end up in a very different state. It's exactly how we do the projection, the prediction of the trajectory. If you are not able to determine which are the exact initial condition, you can end up in a very different final state. Now, we finally had the first forecast. It was much later in the first ENIAC computer, and it needed more than it was fed by electricity power more than 15 houses, and there's less power of digital clock today. So it was really a big effort to produce the first 24-hour forecast. And it took the same amount of time. So for a 24-hour forecast, they needed 24 hours computational time to compute the solution of the equation. So basically, it was useless, but it was very important to show that it was possible to solve this equation and make a weather forecast. So what is a climate model and what are these equations today? So we know how to solve this equation now, and they are the basic equation of the conservation of the momentum, energy, mass, and moisture. They are all of those, plus the equation of state. You can see here all the terms. We can solve the fluido-hydrodynamic equation in many points of the Earth's surface, and then we can exchange information between one grid point and the other point. So to be able to do this, we need to discretize the equation over a grid, and this is an example of the grid that we can use. And for each point of the grid, we can solve the equation, and the grid, keep in mind that is a three-dimensional grid, so it's horizontal and also vertical. If we do so, you can imagine that there are a lot of parameters we need to determine, and we need a very powerful computer. So why do we want to do this? Because we need to know the status of our climate system in all the points of the Earth. We need to have the evolution of our variable in time, but also we need to go very, very, very in depth to know the characteristic of our climate system. So what does it mean we want to know very, very in depth? Means that we need to decide which is the size of these boxes. So this is now the same box as before. We need to decide which is the size of the box we want to use, because the size of the box will determine the characteristic of all the state variables for all the space that is inside this box. So if I decide to use this size of box, that just I overlay this to the Friuli Venezia Giulia map to understand how big it is. So this is basically something like maybe 25 kilometers, not really a real box, but something like that. Everything that is inside the box will be constant. So if I define a value of temperature or pressure or wind in that box, this means that all the points within this box will have the same value of temperature, wind, and pressure.
Is it clear that you can use the same equations no matter what is the size of the coarse graining box?
Yeah, it is.
It is clear?
Yeah, because they are state equations. You can solve them with a discretization that is the correct one, with a grid that is the one that is stable when you integrate your numerical equation. You can solve all these equations, whatever is the size of this box. Plus, you need, if you want to have more details, this equation will not be enough to completely solve your system, because there are some of the process that you cannot describe, some very small scale process that you cannot describe by using this equation. And so for this process, you need to use some other equation that are parameterized equation. But this is another problem for today.
Also, you need some boundary condition on the top of this grid, right?
It depends, I mean, on this particular grid, yes. But if I think about the global model, I do not need the boundary condition, because the global model is a grid that is fully connected. So I just need the initial condition of my
The
system.
vertical dimension does end at some point in this grid?
It ends at some point because the atmosphere becomes much less dense. So at this point, you can basically use some filter, so you can relax the solution to infinite,
okay.
and then the system will work. Okay, so we can decide how big we want our boxes. And by the definition of the size of the boxes, we can go really with the lens to look at the specific physical and dynamical processes that are happening at the grid scale level. And so, for example, I can process and I can reproduce the exchange of fluxes of the vegetation with the atmosphere. I can reproduce the local circulation in my box, and I can use subgrid process. I can do many things, but of course, the more I zoom in, the more complex is my system, okay? Because I add complexity to my system. And then the other thing is how many process, which details, so which process do I want to include in my in the description of my climate system. So I can start, as you were asking before, from the global status of my climate system. So I can start from an instant in time, which I know which are my boundary conditions from the global. Then I feed my, let's say, coarse grid at the boundary with this boundary condition, and I find the solution in this other space of my surface of the Earth, and I can repeat this more and more times so that I can reach really very high definition for a smaller portion of my surface, and try to reproduce some of the process, like for example the convection, the formation of the clouds, without using this parameterization that we spoke before, because usually these are the processes that are parameterized in my model, but I can try to reproduce this process explicitly. But then I need to really have a very small grid, and that means a very high resolution. And here we are. So the smallest is the box, the higher is the resolution, the more accurate I can be, and the more accurate will be the solution of this equation for a single grid point. So in general, what I can do to describe the evolution of the climate, I can use general circulation model that are the model that cover the whole Earth's surface. I can, for this, the size of my box can be between 50 and 250 kilometers. So you can see it can be very large. These are, let's say, cheap model, because the bigger is the size of my boxes, the fastest they are, and the less computer resources they need to be integrated. Or I want to go to very much more in detail, increase the size, decrease the size of these boxes. And then if I want to do this, I need to downscale this to the local scale. So I need to use a technique that allows me to downscale this information to the more local scale. And then if I do this, then I can reach very high resolution. that are approximately close to 1 kilometer, I can use a model that is limited, so it's just on a small portion of the Earth's surface, and then I can derive the boundary conditions from the global, and they have the same equations, so the same physical basis as the global model. Now, today we have reached a resolution that are very high, that it was impossible to think about before, and we are going down to resolution closer to the resolution of the usual weather forecasting model. The weather forecasting model are the ones that are run every day to give you the forecast of tomorrow. But in this case, we are running this model with this resolution to make a climate projection. That means more than 100 years of simulation on the whole region that I'm interested to. This very high resolution model have the advantage that, for example, can reproduce the convective process. You can see that the formation of clouds. This is an animation of a real solution of one of our models. They can reproduce the rising of warm air of the atmosphere, the formation of cloud, and eventually of precipitation that you see underneath following. And they do not need the use of the parameterized equation. And why is this important? Because we know from sensitivity study that when we want to go to scale of 100 years projection, like we normally do with the climate projection, the parameterized equation, and specifically the convective one, are the major source of uncertainty. So the point in which I end at the end of my trajectory is very much influenced by the parameterization I'm using to represent the convection at that scale.
In this simulation, is the grid always fixed, or you have adaptive grids?
In this is fixed, but you can have adaptive grid as well.
Qualitative difference with weather forecasts?
For the model?
Yes, between this downscale model and the weather forecast.
Okay, so the numerical technique is the same. The model that do weather forecast usually are not bothered by the long time projection. So they do not optimize the model for having a statistic of the weather. So basically the climate, when we do climate projection, we want to capture the exact correct statistic of the weather, right? So we are in Trieste, so we want to be able to represent how many times in Trieste in average, what is the distribution of your precipitation, of your extreme precipitation, of your temperature, extreme temperature. This is what I want to do with my climate model. The weather forecasted one, they do not optimize this.
Okay, how do you optimize this? You're going to explain it later.
Not really today, but you optimize this by running your model many times and looking at the sensitivity of the statistic to the change of those parameters that we know are sensitive for the statistic. Like, for example, the convection.
So you're not just solving the equations you saw before, okay?
No.
Some other optimizations.
You optimize this. Okay. So at this point, then, as we already spoke, when I have this technique of downscaling, I want to do also my climate projection. So I want to start from a point in the past and run the simulation all up to the end of century. This is stopping to the present day, but eventually I want to go to the end of century. I want to be able to include the forcing that are natural, but also anthropogenic. So I want to perturb my system. So I have to run my simulation more than one time. And typically what I do, because we need to estimate the uncertainty, so we need to estimate how big is the distribution of my future projection, I need to run my model many times. So this, for example, pink red band is the spread of my many simulation that I repeat to be able to estimate the uncertainty. And the uncertainty of my signal will be the distribution of this particular variable in the space of the solution that I find at the end.
Excuse me, the peak, the 40s has a certain meaning or just?
No, this is a fake one. It's just a cartoon, but it can. It's just due to natural variability because
In what period? Figure?
The natural variability.
Yes.
So it's roughly between. It can be depends on the process you look at. You can have a 5 years, 10 years, 20 years period. Depends on which are the forcing that you consider. Okay, so the oscillation of the line is normal. This is the natural variability of the climate system. Okay, so as you can understand, if I want to do this exercise on many regions of the world, so like this is Europe, Africa, and so far and so on, I need a lot of computer resources. And if I stay with a grid size between 12 kilometers and 25, 50, I am okay. I do have today the computer resources to make many times the same projection for more than 100 years, typically 130, 150 years for a single projection. But if I want to do a resolution that we call convection permitting, that is the explicit representation of the convective process, and I want to do 150 years, I cannot do this. I mean, with the actual computer resources we have, and especially with the storage that we have today, this becomes something very extreme. So then, at this point, the scientific community, okay, so this is an example of how many terabyte and CPU I need for a normal simulation of 25 kilometers for 150 years. So you have already 100 tera for one simulation, multiply this for the number of simulation, number of domain, the number of time you do it, and you can understand that it's going to explode.
Can I ask?
See.
So this projection for 120 don't take into account the concentration of elements in the atmosphere, the change of concentration.
You means the greenhouse gases?
Yes.
Yeah, of course. This is what I call, so the red band that I showed you before is the one that is the projection made with, and in which we assume there is an evolution of this emission. That
so there's a model on that as well.
There is a model on that as well.
Okay.
Yeah. So within the climate model are a lot of subsystems in which you need a model. Like, for example, the interaction with the land surface, the convection, the chemical model can be there, and the ocean as well. So you have a fully coupled system when you do this. Okay, so at this point, we can invoke the help of the artificial intelligence, but with a caveat. So we reach a point in which we would like to have a lot of projection in time, very high resolution, but we cannot do with the actual HPC resources and computational resources we have. So at this point, I like to cite something from Dostoevsky, that is in Italian, is a translation in Italian, in which he basically say that once we have discovered all the functionality of our brain, basically there will be nothing left for us to do, and there will be not any more action, neither adventure for us. So we have to be careful when we move to this towards this direction, and we think that artificial intelligence and machine learning can solve all our problems. And now I show you a slide that is very close to me, that I start to use from the beginning of my work in this field. And I cite another another sentence from Santiago Ramon Cajal, that was the first neuroanatomist that was able to draw the shape of the connection of our brain. And then from this, based on this, then the theory of the initial neural network and machine learning was shaped, and and basically what we tried to do was to mirror the function of our brain. And just out of curiosity, I think maybe you all know, but it's nice to recall that the first really machine learning technique was already there in 1961, when this little toy was invented, in which basically each matchbox for each possible game position. So we are trying to teach to this collection of matchbox to play this game that you all know, and then at the end, by simply opening and closing the matchbox many times and changing the number of color bits, you can teach to these boxes to play this kind of game. But now we have evolved from that time, and let's see how machine learning can help climate. So we, in our field, we start to use machine learning in the early 19, and usually, and what you commonly find in the literature is they are studying using machine learning for forecasting weather or for statistical downscaling. So for deriving the distribution of a specific variable in a specific point in space. But in the meantime, the climate science has generated a lot of data. So you see here, there is a graph of the projection of climate data volume increase. And we see we are here, and the projection is going to be much worse in the future. And having so many data generated every year, and every 5 or 6 years, a lot of this data needs to be analyzed, for example, to make a new climate assessment, then we really need to speed up and find a way to analyze them. So usually why we think that machine learning is suitable for our problem, because the performance of the neural network to deal with images is and also with the estimate of nonlinear relationship as something that is very much interesting from the climate and weather community. We also add that this development of the convolutional layer are really very optimal to analyze climate map, and because the different variable can be considered as different channel of this image. And one of the initial application of this was precipitation nowcasting. That is something that is very, very difficult to do, as you can see, on a point level, on a very localized scale. And after this initial approach of the 1980, the second attempt was to use this neural network to detect and classify meteorological objects. Then, later on, only in 2017, there was a convolution. There was somebody that introduced a convolutional neural network architecture to develop an automatic and efficient method to detect in climate simulation extreme weather pattern. So we are already to something very close to the activity we do today. So in the initial application, what we tried to do by using machine learning was, for example, doing the estimate of rainfall on the ground based on the station data that we have. In region like Africa, the problem is that you have a very sparse network of data. So you have station, you see the coverage of the station is very sparse. And the only method that you have to estimate the rainfall over there is to use satellite system. So we took advantage of the many satellite systems, the geostationary and the coverage, the other one, the rotated one that now doesn't come to my mind the name. We use all this data, and most of the algorithms try to derive a relationship between the observation of the space and the observation of the precipitation on the ground.
So you mean the polar, the one who goes
the polar,
okay.
Right, the polar one.
Because there is an angle, a latitude angle above which you cannot use the geostationary, right?
No, because the geostationary as a length is the infrared length, and so you can only observe the top of the atmosphere clouds. So you are going to observe only the cold cloud that are at the top of the atmosphere. Whether they're just the polar orbiting one, they use the microwave, and then they are able to penetrate the structure of the cloud and the system, and can give you much more detailed information of the amount of water that you have into the cloud. And so it's a different. So we try to do this at that time, but to be able to feed our machine learning algorithm with data, at that time we had to try to compress our the amount of data we had, for example, using the principal component analysis that everybody was using at that time, to be able to feed our network and get our estimate of the precipitation. Why did we use the artificial neural network at that time? Because they are good in feature extraction and classification, but as we know well, at that time they need a large amount of CPU and a large amount of man hours to be able to get some reasonable result out. But so this was the network we were using at that time. So just was a simple Fortran program with few library call. And what we were able to do was something to build a network of this size with this kind of layer, like a maximum 3-4 layer with this amount of nodes, and try to train this network to invert basically the information going from the top of the atmosphere down to the ground. Here you see an example that just to show you how it works. So this is the algorithm based on the machine learning, on the neural network. This is a more standard one algorithm. That is a statistical one. You can see a regression. These are different resolution in space. So you have the grid point level, then you have some averages after some averaging in time and in space, and this is in time, and this is the averaging in time and in space. You can see that the better performance of this network is visible at this scale, not very much at the very fine scale of the station at the point level, but then when we average over time and over space, then basically we already lose the advantage of using this kind of algorithm. And spatially, if we want to look at the comparison, but if we look at the comparison spatially, so how the two things perform, so this is the machine learning one, and this is the more standard one, you could still see that even if not completely, it is not completely reproduced by the statistic, in which we do not see at very large, when we assemble the spatial scale and the temporal scale, the advantage. But if we look at the point-wise and single time step in time, we can see that this algorithm is able to reproduce the observation better than the other one. But this was basically the history, and we move forward. But there was a gap between that period and today period. So there was a 20-year gap between the development of the backpropagation algorithm that was the key milestone in the development of this algorithm, and then the boom of the neural network in the early 2010, when the climate community started again to use this kind of technique. And why was that? Because first of all, there was a new activation function that was invented or tried, compared to the normal function that were usually the sigma function or the step function. And this was speeding up basically the training of the network for very, very large data set. Then in 2009, there were two major publications coming out, and they were about the creation of a new kind of network, the ImageNet, that was the first convolutional neural network. It was explicitly designed to deal with images, so visual recognition and classification. And then later on, of course, there was the development and the starting time of the graphical process unit that, of course, were an optimal GPU architecture to train the neural network. And only at this stage we could think again as a climate community to go back to this technique, because before it was impossible for us. We already reached basically the bottleneck, and we could not handle all our data with this kind of algorithm. So the most commonly used architecture that we are using today are this convolutional neural network. I will go a little bit fast now because I want to show you the result, because they are optimal, as explained before, for our kind of data, because our kind of data can be treated as images, and in particular one kind of network that is the recurrent architecture, so you cannot really read above, because this kind of network is it's able to extract important information and encode in the space in a smaller dimension, and then inject this information into the expanding one. So basically you start with a very high dimensionality, you compress the information, you process, you extract the information that you need, and then you go back to the higher dimension that you had in the beginning. So let's then see how we use nowadays this network. So let's think back on what we told in the beginning. So what we want to do is try to create projection of the climate system at a very fine scale. So we want to go from the large scale information to the very local scale information. We can do this normally with dynamical downscaling model that are the regional climate models, so the model that act on a limited portion of space. And if we start from those to think how we can use machine learning emulator, we can start from this assumption. So the RCM so the regional climate model can be seen as a function f that creates a high resolution simulation y from a low resolution 1x. So according to some famous modeler, it can be decomposed, this transformation, it can be decomposed as a large scale transformation and a downscaling function. So this function that I use can be decomposed in two parts, a large scale transformation and a downscaling function. What does it mean practically? So this is my original large scale information. I can do a large scale transformation, so you can see that basically the features are similar but not identical. And then I can add on those a downscaling term, a more local scale details that I need to be able to know the state of my climate system at the local scale. So if I do this, I can try to use a machine learning method that is able to basically emulate this function. So I will ask to my machine learning method to emulate my regional climate model and try to create this mapping function that will map the large scale into the high resolution scale. Of course, I will do this. So I will start from my large scale simulation, the global one. I will create a real downscale simulation. So I will downscale dynamically with the equation my large scale simulation. Then I will upscale this regional simulation. I will use the emulator to reproduce by using the upscale simulation the target output, that is the RCM simulation created dynamically. I can do this in several steps. I will first train, then evaluate, and then I will use it in my application. Which are the application? Why is this important? Because if I am able to extract an emulator based on machine learning that is able to create the mapping function from the global to the regional scale for a specific couple of GCM and RCM, I can extend this emulator to all the other GCM that are available, and I can try to create an ensemble bigger and larger than what I could have done with the simple dynamical downscaling, because this approach is supposed to be cheaper in terms of computational time. And I can also gain in the estimate of the uncertainty, because I can expand the space of the solution that I will have at the end.
Do you know it generalizes well?
Because I tested.
Because you try it every time.
No, I show you, I test it and see if it works. Okay. So what I do, I can do this on two simple variables like the temperature and the precipitation. We will focus first on the temperature and see if my method is working. So which are the input of my system? So for this kind of exercise, I'm using the AirNet network, the U-shaped one. And the input of my system are the 2D input, so are all these images up there that represent the status of the atmosphere in the region where I'm interested in. In particular, they are geopotential height, temperature, humidity, and the wind, eastward and northward, plus some information at the surface that I need, like for example, the temporal information, the mean and standard deviation of the X component. I normalize my input, and also I use the topography. So I tell to the network for each of the grid point, which is the height of this grid point. Once I do this, I can use any kind of network. In this case, we use the convolutional neural network with the U shape, and that is this one. That is something adapted by Ronenberg et al. So we do this, and we train our network, and then we evaluate our network. So we remember that the input of our network are the regional climate simulation, so are the data from the proper dynamical downscaling, and this will be upscaled to the GCM resolution. So basically I do, I degrade the signal, so I bring down the RCM resolution to the GCM resolution. So basically my box, that is the smaller box that usually I have for the RCM, becomes a bigger box to match the GCM resolution. Then I do this, the perfect match with the RCM simulation, and try to see if what I get is reasonable. So this is my actual field. So this is the temperature field of my actual RCM simulation. This is the upscale field from that. So you can see the size of the square of these two simulations. You see that this is a finer grid, this is a coarser grid. Once I do this, I use this as an input of my network. I train my network, and I look at the result of my emulator in testing. So of course I do this not with the same sample, so I use the cross-checking. And as we can see that starting from this, I am able to reproduce the high resolution structure. You can see the mountain. Of course, I have lower temperature in the mountain, both the Pyrenees or the Alps. I have the correct range of temperature and almost a perfect spatial correlation. If I look at the time series evolution for a region in the Pyrenees and the Balears, as well, I see there is a perfect match between the emulator and the truth, that for me is the RCM, and see. And so I can say that there is also a good reproduction of the local temporal variance, because I see that there is the exact oscillation of my signal. So I can also use the score in 2D. I can look at the temporal correlation and the variance ratio, and I can see that the two fields are very well correlated in time, and also the variance, the explained variance, it's very good. So in this exercise, I can see that I can repeat this for all my couple of GCM RCM. This result extends to all the simulation with a bit less accuracy if I change the GCM. So you remember I trained this machine learning on a specific couple of GCM and RCM, and then I assume that the method has learned the relationship between the large scale and the finer scale, and then I try to use the same for other GCM to expand the model ensemble. What we see for this specific exercise is that the accuracy, so the score of my algorithm, is a bit less when I change the GCM. So when the driving field, it's different from what I've used during the testing phase.
Say a bit less. A bit less is,
I mean, it's a bit less
10%.
means that if you look at the temporal correlation, is not systematically 1 like in this case, but you can be between 0.9 and 1 or 0.8 because the temperature variable is very easy to deal with. And also the variance is a bit more degraded, it's not optimal like this, but you can still, I mean, you are within the range of the uncertainty of your projection.
So if you move to Africa, let's say you take the same.
We are not there yet,
yes,
because for Africa, very high resolution is very demanding. So we have, for Europe, we have this result. For Africa.
To another region. So it's my question about generalization. So
okay, if you move to another region, so this is a specific region in Europe. If you move to another region, you get the same result. So the spatial generalization is okay for a region like Europe. Now, if I move this system to the tropics, the answer I don't know at the moment. We didn't do yet. Okay. So then we can do this, of course, also for other variables. So the temperature one is a variable that is easy, but there are other variables like the precipitation that are much more complicated. I can try to do this, and I can use a different approach. So I can use a perfect prognosis approach in a real model framework. I can start from, again, the input of a 4D spatiotemporal input, so the same image at different time step with different kind of variable, and I can try to match the high resolution. So I need to downscale those information coming from the large scale condition of my system to the ground, in which I want to have a very high resolution, a very detailed description of the precipitation field. So basically, I want to do something like that. I want to use several height in the atmosphere and several variables. And then I want to try to train an algorithm in a way to get a resolution of 3 kilometer precipitation over my, for example, the alpine region that I showed you before. I can do this. I will skip this part. It's a very difficult problem because the precipitation is a variable that has this distribution. You have a lot of events that are 0 and few events, only 10% of the image that we have precipitation inside. So it's a much more tricky problem. And indeed, I just want to show the architecture that we are going to use this time is much more complicated. So we need to have a classifier and a regression. We need to have a two-step process. First, to classify my object. Second, to estimate the value of the precipitation. I need to use a convolutional recurrent network plus a graphic network, that is this one, a grapho. So as you can see already from the structure of the algorithm that we need to use, you can understand that the problem is much more complicated. And then the answer is, can we, let's skip the details. Can we reach some results that are reasonable? Okay, so this is the comparison between the reality, so what is called grifo over there is the reality. This is an easy statistic, so this is the mean precipitation over the whole year. You can see that the network is able more or less to represent this, so you can see the shape and the intensity is not bad. If I move to the seasonal distribution, still I am okay. So I want to divide in summer, winter, spring, and fall. I'm still okay. We start to see some difference. So there is some bias between the two. But when I go and try to estimate the extreme events, because we are doing this because we want to get at the extreme events that are happening over our region, you can see that at this point, the performance of this specific algorithm are a bit less. So the intensity of the events, so this is the predicted one, this is the observed one, is less. The spatial distribution is fine, but the intensity is less. And then the final question, and I will stop, is, but is this algorithm very far from the model? I told you that usually we run a lot of models, different models, we create an ensemble. So this is the observation for a specific extreme event in November 2002. These are the observations. You see there are three core of extreme events. So these events was hitting Italy in three different parts. These are many models. So it's for 15 models that are trying to reproduce this in a convection permitting mode, so with a very high resolution. You can see that the distribution of the precipitation is very, I mean, they are all raining in the correct place, but the intensity is not the same. If we mix up among those models our machine learning result, I would dare to say that it's not really different if we mix this with the ensemble of the model, right? I mean, it doesn't stand out as something very, very wrong. We have an underestimation, as we have seen, but it's not so, I mean, different from the other. So this is where we are. The world climate community is there, is trying to optimize those kind of algorithms, trying to get a maximum number of projection, the most accurate possible, and the highest resolution as possible. And some references if the people are interested in the work.
Erika, for a very nice talk. Questions?
I have a question on this last part. So if I understood correctly, the basic idea is that you know how to run a model with a coarse grid for a very long time. And you would like to do that ideally also with a smaller grid, but you cannot do it. So you get the snapshots with the coarser grid, and with the model sort of convert those to a much more accurate forecast with a smaller grid. Is it more or less what happens?
No, so it's not that I'm not able to do. I'm able to do. These are models. These are high resolution model running with the small boxes. You know? But the problem is that if I want to run many of these models for 150 years, I cannot do it.
No. But let's say ideally you would like 100-year simulation with the same accuracy, which means with the same small grid of a 24-year. The question is, so this means, so to make it work, it means that given a coarse grid, there is a one-to-one correspondence, if you want, with what happens in the smaller grid. So in principle, you know, if you look from like an image, if you have 10 pixels, you know, there is a certain entropy, so there is a certain possible configuration. But if you have 100 pixels, in principle, there are many ways you can interpolate from one to the other. So I was wondering if there is any mathematical, say, background that says, well, I mean, there is no entropy, in the sense that there are no multiple microstates corresponding to the small peak, small accuracy that correspond to the same coarse grid. I don't know if
the answer is
if I explain myself.
No, because exactly this is the issue of the uncertainty. Because even when you use a dynamical model for downscaling, so from going to the large scale to the small scale, you need to use a dynamical model. So you need to solve your equation for the small boxes. Even in that case, there is a lot of entropy because you do not have, if you solve the equation in 2, 3, 4 different models, there is always a difference between the model. So when I say, when I show you before that you need an ensemble of models doing the same exercise, solving the same equation for the same grid point in space, to be able to estimate the uncertainty is exactly that, because those models, because the equations are the same for all the models, the basic, the state equation, but the parameterization one are not. So the uncertainty that comes into my system, it's due to the parameterization of some physical process. So there is not even in the dynamical world a one-to-one correspondence. Of course, there is in the reality. In the reality, if you use the observation of the atmosphere and you want to estimate the precipitation in a specific point, in the reality, there is a one-one correspondence because the extreme events it's happening in Liguria, but it's not happening in Tuscany in that specific day. But this is why in this second example, what we try to do is we try to learn from the reality. So we do not use the model, but in this case, I didn't have time to explain, we are using the perfect prognosis approach. So we start from the observation of the atmosphere, the best we have, that are called reanalysis. So they are still model output that are very accurate because they do assimilate observation in their model. And we train the network with the observed precipitation. So we are trying to constrain our algorithm to the reality. But still, we are not there yet.
No, I mean, maybe like, I don't know. Okay, so let's say you know that in the county of Udine it rains. Okay, let's say you have this level of. Then it could be because it rains in Udine or because it rains, 50 kilometers apart. And from the point of view of this coarse graining, the two situations are exactly so they are no different.
Within the grid point, there is no difference.
So my point was that maybe if you those two events are compatible with the fact that in the county it rains. So this is why. So if you only know that it rains in the county and you want to know exactly where, well, you need to learn how to map the two. But it could be that in principle there are multiple outputs and they are all good.
Given the limited resolution of your input, yes, you could have multiple solutions that are equally good because also your input have a limited resolution. So yes.
I see. Thanks.
I have a question, very naive. When you show very long time prediction, what initial condition you take? Now backward in time or at the beginning forward in time?
For the climate projection, you mean? Okay. So the global model, what they usually do, the global model, they are fully coupled system. They do not know anything about the reality. So they don't know today what is happening. The global model, they are the atmosphere model interacting with the ocean and interacting with the river. So those models, they are integrated for hundreds and hundreds of years.
With what initial conditions?
With any initial condition, because you have to reach a stable condition, a condition for which all the three systems are in equilibrium and the exchange of mass, momentum, and blah, blah, blah is in equilibrium. At that point, you decide this is my starting point, and I assume this is, for example, the year 1900. But there is no correspondence between the real year 1900 and the one of the model. It's only true that the statistic of that model, so that model that is in equilibrium, that has reached the equilibrium, is able to reproduce in average the climate statistic everywhere on Earth. So it's able to reproduce, for example, the episodic of El Niño, that are this warming of the water in the Pacific, are able to reproduce the movement of the storm track. So we see the precipitation band moving up and down. the cloud system, the formation of the cloud system, the event, the distribution of temperature, precipitation in every location. This is what the model does.
And I missed here in this model, so here what initial condition you take at the beginning of the month?
No, these are models that are on the smaller domain. So these initial conditions are taken from the global one. So
you have the data at 1st November, I don't know, 2002. You could use that if you want.
So in this specific example, because we are running the model not in a projection, we are running the model using at the boundary the reality, so the real world. So because we want to test the model, so before you run a projection, you have to test your model and you have to make sure that your model is working in the real world. When it's working, then you go in the projection. In this case, the boundary conditions are given from the reanalysis that are the best approximation of the reality.
And my eyes are not very well working. In the average, there is something near Venice, which is like, which I don't see in the others. If you do the average, I don't understand why you get that.
No, this is not the. It's just it's the coastline. It's the drawing of the coastline.
Okay.
It's black. There is no green.
Okay.
It's just the coastline.
Okay.
So you don't see her because the drawing of the coastline is a bit different. But it's
just
not.
graphic.
No, it's yeah.
Sì, però diciamoci.
Is a higher resolution of the coastline.
General question. So you have these physics-informed neural networks, which are, say, mesh-free methods to solve partial differential equations and so on, include dynamics. So is your community using them or trying to use them as an alternative way to solve the equation?
Okay, so every model is it's based on this fundamental equation, but the way to solve this equation can be different. So you can have the grid that are zooming in and out. So there are mesh grid that are concatenated. They have different resolution. You can use Lyapunov exponent to discretize your equation. I mean, there are many methods that you can use. But still, the equations are those that you try to solve.
So I was thinking about physics because they are mesh-free. So in situations where you have scattered data, they may be useful. Maybe
they use also this mesh-free, and also they use something that is called adapted mesh or something like that as well. But I mean, in the world, we have at least 5 centers that create global climate projection, and they use all different methods to integrate. But the final result, it can be more or less accurate, but it's not really. It doesn't really depend on the way in which you discretize your equation. If your system is, I mean, if your discretization it's good and your system is stable, then what it really matters is the way in which you represent the physical process.
Yeah, it's also a matter of efficiency, right? Because we want to be, this is the key point, you know? We want to fit something that it's working fast.
Yes, but this is more the issue for the limited area model, because for the global model you can use all this technique. When you use the limited area model, so when you have a square, it's not so easy to use different kind of discretization, okay? Because you have the boundary that you have to treat.
There's a question.
Yes, I have a related question that you directly use machine learning technique to solve this 3 dynamics equation. That means given initial condition, you don't need to solve this dynamic equation, and it directly give you the predict at arbitrary time.
And the answer is, how would you do that? Because you need to solve this equation for every grid point. So this means that if you want to use machine learning method, you need to have the perfect input and the perfect output for that point. And you do not have observation everywhere in the world and at any level. So I mean, you can mimic probably a model, so you can use the data from a model and try to see for each of the grid point if this is possible. But I don't know how much you would gain in terms of speed and computational efficiency to do that.
last time when I told my friend is working on applied mathematician. It's like one of his friends is working on this topic. So directly using machine learning to solve equations. So
yeah, I mean maybe this would, I don't know. We need to see how fast you would be to do that.
A question on the previous slide, which is like the one with the actual model. Maybe the one before. Here, you said you have a classifier. This to recognize whether you have precipitation.
Yeah, it's like a switch. It's like, is precipitation yes or no? Because most of the data, unfortunately, the distribution of the precipitation is very skewed, and most of the data that you have are 0 or very close to 0. So by using this double architecture, you can optimize much better the loss function.
Maybe you can treat the extreme event case as a separate problem. So because rare events are sort of a special case, right? So what if you just train the thing to reproduce extreme events and you don't care about, you know, the bulk of the average statistics? So because that's a different problem. Right? Yeah. So
because extreme events, what you call extreme events, it's something that is the 99.9 percentile of your distribution. Right. So guess how many, but the guess how many you have in a grid point?
Very few, but let's say.
You don't have enough data to train.
But still.
No, you don't. We tried, but I mean, it depends on what you really want to do. If you want to optimize your network for a very specific region for these very extreme events, you end up for 10 years to have 3 events. So it's very, very difficult to do it.
Maybe you can start with less extreme events.
You simply go back. What you do, you just simply go back.
So it could be an option.
You just move your line up there, and you will have this.
So instead of picking the whole distribution, maybe it's just pick the tail and maybe get more, let's say, more accuracy over there. Which is what you care about, right?
Yeah, you can do that without discarding those events, because you can use a loss function that has different different weight according to which part of the distribution you are. So we are doing this, but still it's a tough problem.
I was thinking, maybe is there any sort of a similarity analysis, so you have different parts of the world that have a similar climate, and you can train your the network on both regions. You know, they say this, for example, California is a Mediterranean climate. I don't know, I'm very new, I'm not sure. But are there a similarity in
Okay, so the training of this network is not done just randomly. So what we use as an input are those variables, those state variables that are usually in the equation that are used to derive the tendency of the temperature, the tendency of the precipitation. So if I think about a different place on the world, I mean, the circulation of the atmosphere is similar, but still not identical. And also the interaction between the large scale and the local scale forcing, think about the mountain, for example, it's very, very important in this case. So a network that is able to generalize so much, I think probably is very difficult.
Other questions? No, if not, let's thank our leader there. Yes. Next would be Fabio Anselmi on the 3rd of May.